Hello everyone, just wanted to go through a presentation that I did at the EECON in 2019. Turns out the video we took didn't work, and I thought it'd be useful for people. It was about designing for resilience and inspection for overhead line design in accordance with NZS 7000. So what is resilience? It's essentially the strength and flexibility of a system to resist permanent damage, but also your ability to detect underperformance before the risk of permanent damage. And it's also your ability to rectify any underperformance before it gets damaged, and the speed at which permanent damage can be detected, and the speed at which it can be remedied if it does occur. So that, combining all that, would give you a resilient design. Quite often as engineers, we just focus on meeting standards, and we don't really focus on the performance of the system as a whole and the management of the system down the track. So to do this, we have to balance the upfront cost, the availability of materials and workmen, cost of ownership, the inspection and the maintenance costs down the track, any replacement costs, the cost of a failure, and the performance specifications. So we need to satisfy the electrical design requirements, the constructability, the aesthetics, and the customer expectations. So how do we do this? We need a cheap product that's fast and easy to install, doesn't degrade, requires no maintenance, and is over-designed and tells you when it's going to fail with plenty of warning. Of course, that is impossible. So how do we do it? It's not really that simple. Basically, we need to learn from the past. Wood has one of the longest histories as a pole and the most research conducted, but it's only been recently that we've actually figured out exactly why wood poles have lasted as long as they have. And this is a graph of a Monte Carlo simulation that I did 5-6 years ago, more. It'd be nearly 10 years ago now. I first started doing this with Leith Elder from Essential Energy. And basically what you've got here is, this is just the results from 2 particular pole locations in a simulation of, I think, 1,000 poles. And what it's showing you, say we picked pole number 1 in the simulation, 1 out of 1,000, and we picked pole number 100 out of 1,000 to do this. So pole number 1, the actual strength over time, is the blue line. Obviously, when it jumps up, that's when the pole has been replaced due to either failure or due to the results of the inspection. And the crosses are the maximum wind load that pole experienced each year. So this is mapped out over 150 years. These wind loads, by the way, are based on AS 1170.2, which is the basis of AS 7000. And essentially they're simulated using the Monte Carlo algorithm as well. And as you can see, funnily enough, when you apply the rules from 1170.2, the 500 pascals that we've been using for design for the better part of 75 or more years, well more than that now, it's pretty close to the money. Most of the maximum wind loads in any given year are around that mark. And that's because when you look at the standards, 500 to 600 pascal wind load has a chance of about 50% occurring in any given year. So safe design is more around this 1,000 mark, and that's got a chance of 63, 65% over a 50-year design life of occurring. And as you can see here, that does occur, a couple of times every 50 years maybe. Anyway, so what this sort of shows, it gives a representation of what, no one wood pole is ever the same as another wood pole in terms of its original strength, its durability. They're so varied, and the original strength is highly varied. We know that through lots of testing that's been done, and we're also now getting more and more aware of what the actual strength is down at this end as well. So basically, when the pole is nearing end of life. So what we'll focus on this pole here. It's a pretty good example. And if we just compare that just quickly to your steel, your concretes, things like that, where your original safety margin for the design of steel and concrete is a lot lower than what you have with timber, just because of the high variability of timber. You've got 95% of your poles that are well above the minimum strengths that you're assuming in your design. So, this here is something that utilities need to consider moving forward, because more and more steel and concrete poles and fiberglass poles are coming in, and they're starting at this sort of strength here. And we have seen cascade failures of basically brand new lines at or just above design wind speeds. So one, it makes you question, okay, are the design wind speeds okay? But two, we probably need to build a little bit of fat into the original design to allow for this strength loss over time as well, because this here is when the strength of the pole really becomes important towards the end of life. So we've got to make sure our inspection methods are linked to our original strength design, so that this value here doesn't get too low, that the reliability of the line drops below a level that we're really interested in, or that we're trying to maintain. So basically, we need to look at building that fat in and moving that up. If we zoom in on the end of life of this particular pole, this is what we're really interested in when we're talking about matching up inspection criteria and condemning criteria to the original design of the pole and to a reliability number that we're trying to hit, basically. So that period there is really, that's one inspection cycle for, say, a 5-year inspection cycle. What we need to do is make sure that when we're inspecting here, it does have enough strength left still by the time we get to that next inspection, that we can actually pick up that point and condemn that pole at a strength where it's still got enough resilience in it, enough strength in it to resist the likely loads over the replacement period. So it might take a year to replace a pole. Once it's been detected, it might take 6 months. Different utilities have different requirements and different schedules they work to. So once you consider that, we need to know, okay, what's the design wind speed required for this pole at the end of life to make sure, one, it's got the same reliability in that final 5-6 years as it did when it was originally put in the ground, so as a brand new pole. And then we need to make sure we've got that same reliability over that that inspection interval and plus the replacement interval. So what does this actually look like in numbers? Basically, if you look at a new pole, 50-year design life, if your design wind pressure on your conductors is 1100 pascals, then if your design life is 6 years, so say a 5-year inspection cycle plus 12 months to replace, then your design wind pressure on your conductors comes down to 784. If you've got a shorter inspection cycle, so you might say at a particular point of strength loss, you'll actually inspect the poles more often, say 2.5 years plus a year for replacement. That's your design wind pressure on your conductors. You might come down to a yearly inspection cycle for certain structures. That equivalent design wind pressure to give you the same reliability, the same risk of a design wind occurring within that final, say, 2 years as what you have for a full 50-year life, then you're down around 606. And if we look at, say, the old working stress design standards at 500 pascals, you're looking at a design life of about half a year. Okay, so when you start looking at these numbers, you can then calibrate your degradation factors to actually, like your degradation factors for your new pole designs, you can calibrate them to match your inspection criteria at the end of life, so that you've got that same reliability across the board. And that is how we build resilience into the design from the start. You may need to look at other load combinations as well in certain situations, but we tend to find that basing it on the wind loads covers most of the situations. In some cases, snow and ice may be more prevalent and more of a factor, but not often. If we consider all these factors and we look at the diminishing design wind speeds, we look at your degradation factors and any other design factors you've got in there, we can calibrate the design to ensure between the design and inspection down the track, we've got a suitably reliable network. Yeah, not so easy. It's a little bit complicated still. You still need to, for proper resilience, you still need to look at strength and flexibility as well to resist permanent damage. So one of the key things in timber pole lines has been the flexibility of the line. And when older poles start to decay and stuff, they actually become more flexible, and that sheds load to stronger poles beside them. Things like that need to be considered when you're looking at other pole materials as well. So I might leave these for another video, but we'll touch on the ability to detect underperformance in the next video. I hope that's been useful. It's quite a complicated little subject when you get into it in detail. It's kind of what I've specialised in for the last 10 years or so, is trying to figure all this out so that we can inform standards and basically improve inspection systems. Recent court cases and things like that are pointing out some holes in historical inspection and design methods. And fortunately, we've sort of done the work now and we can start to plug those holes. So hopefully this is useful. Yeah, I'll catch you later.